In this video, we look at another example of hypothesis testing for one proportion. We know from looking at box plots that births are not even for each day of the week. Visitors at a hospital claim that 15% of babies are born on Wednesdays. Researchers at the hospital decide to conduct an investigation to see if this claim is valid. In a random sample of 235 women who gave birth at the hospital last year, 49 of the births occurred on Wednesdays. Researchers are interested to know if the birth rate on Wednesday is significantly higher than the rate claimed by the visitors. Our first step is to set up the hypothesis. We are going to use P to represent the proportion of births on Wednesdays, and we are going to use decimal form for proportion. So we are going to say 0.15 instead of 15%. Our null hypothesis always has equality, so our null hypothesis is a statement of the claim that the visitors made that 15% of babies are born on Wednesdays. So for our null hypothesis, we have that the proportion equals 0.15. Our alternative hypothesis is this claim that researchers are interested to know if the birth rate on Wednesdays is significantly higher than the 0.15 rate. So we write our alternative hypotheses as P is greater than 0.15 here. So once we have our hypotheses written, our next step is to collect the data. So we can calculate the sample proportion. This is using the data from the random sample from the hospital. So our sample proportion P hat is 49 out of 235, where 49 was the number of births that occurred on Wednesday out of 235 births total in that random sample. And then we convert to decimal, and I like to round to 4 decimal places. So that would be 0.2085 as a decimal. So we see that does look to be just eyeballing it higher than 0.15. We can't say for certain without doing a hypothesis test if that difference is significant or if it's something that might have happened just by chance, since we know that there's variation anytime we do a random sample. Our sample size N is 235. And then we're going to calculate the standard error. Since we have 0.15 as the given value in the claim, we use that in our standard error. If we use the sample proportion value, that would be called the estimated standard error. So calculating out our standard error here with the 0.15 times 1 minus 0.15 divided by 235 and then square rooted, we get 0.0233 after rounding to 4 decimal places. And then I put a note here, use the P given in the hypotheses. And my note got cut off a bit at the side when I scan the document, but you can see that that 0.15 comes from the null and alternative hypothesis. And remember, we always have the same value in our null and alternative hypothesis for comparison. Our next step 3 takes us over to StatCrunch to work the formulas and record the evidence. You could, of course, always do the z-stat or z-score formula by hand and then consult with StatCrunch or a table to find the p-value, but we're going to go ahead and let StatCrunch do all those calculations for us. So in StatCrunch, I can open a blank StatCrunch, and then I'm going to go to Stat, Proportion Stats, one sample with summary, since I have the data counts already from this study. And so a success is what we're counting. In this case, it's births on Wednesday. And it's important to say we checked to make sure we had at least 10 in this group, so that went without saying. But since we had 49 births on Wednesdays, that's more than 10. And the other days added together, the not Wednesdays, are also definitely more than 49, since it's out of 235 observations total. And so now, setting up our hypothesis, we are going to change from the default 0.5 in StatCrunch to the 0.15 that we're comparing to. So notice how StatCrunch automatically fills in 0.15 for both the null and alternative hypothesis. I really appreciate that. So StatCrunch sets it up so that you cannot make a mistake with your value. You need to make sure you have the same value in both hypotheses, since these are competing claims. And then we're going to choose the appropriate inequality for the alternative hypothesis. Researchers are checking to see if the birth rate is significantly more than 15% or more than 0.15, so we use the greater than inequality. I like to see the p-value plot, so I always check optional graph down here for the p-value plot, and then we can click compute to see our results. So we can see here the 49 count out of a total 235 gives us a sample proportion that matches what we calculated by hand, 0.2085, and the standard error that matches what we calculated by hand, 0.0233 if we round. And then we see the z-stat is 2.5 or so more than 2 standard deviations, so we're in what we think of as unusual territory. And our p-value is 0.006, so much less than the 5% or 0.05 significance level. We can arrow right to see the distribution plot here, and we see our right tail because we're doing the greater than inequality in our alternative hypothesis. And we see that we are beyond 2 standard errors or 2 standard deviations on this chart, so we see we're in unusual territory. So we are going to record these and do our analysis. So back here in step 3, I've written down the z-stat or the z-score, you can call it either term, and the p-value 0.006. So notice that p-value is below the 5% significance level. We're using that by default because the problem didn't direct us to use any other significant level. Sometimes you're told to use 1% or 10% depending on how accurate the researchers want to be. And then we need to state our conclusion. So because the p-value is below the significance level, we are going to reject the null hypothesis. So what that means in terms of this problem is that there is sufficient evidence to conclude that the birth rate on Wednesdays is significantly higher than 0.15 or 15%. Another way we could interpret this is to say if the birth rate on Wednesdays was 0.15 or 15%, we would be surprised to see results like what we saw in this data from the sample of 235 births randomly selected at the hospital.